Hello, I'm Soudeh and with me is Michael. Today we will be speaking with you about our paper, Privacy Preservation and Implication of Machine Learning. We will start by briefly highlighting some of the background of our topic and its significance. I will talk a little bit about our background. At first, the collection of digital information by different organizations has created tremendous opportunities for knowledge-based decision making. However, it has also increased the concerns over privacy. In response, various techniques have emerged which we call privacy preserving data publishing or PPDP. Similarly, and related to this, is privacy preserving machine learning or PPML. There are some database tools that can be used to employ some of these aspects of PPML and PPDP, which will be mentioned later. In a typical scenario of PPDP, there are two phases. This process is described in Figure 1. In the data collection phase, a data publisher receives data from record owners, for example, hospital and patients. Then in a data publishing phase, a data recipient collects the data from the data publisher. The data recipient could be an attacker. So before data publisher publishes, some privacy preserving techniques should be applied. PPTP is often applied as a generalist approach to privacy preservation where downstream application may not be known at the time of publishing. The expectation is that standard data mining techniques can be applied on the resultant data. Um, with the emergence and increased use of machine learning, a new suite of threats now exist that present a challenge to PPDP. Often these applications use private data to extract patterns and build models. In some instances, machine learning has the potential to reveal sensitive or individually identifying information on previously anonymized data. In an increasing need for computation and storage for running machine learning also has led many companies to cloud-based machine learning as a services or MLAAS. So users, in order to train machine learning models, and in some cases store their machine learning models, use cloud service providers. As a result, it makes their data vulnerable to be stolen by attackers. As a result of these new threats from machine learning, PPML has emerged with a focus on providing more specific techniques for addressing some of these vulnerabilities. The effectiveness of PPTP and PPML techniques in maintaining privacy in the face of downstream machine learning application is significant because as machine learning becomes more prevalent, so do the potential risk to an individual's assumed data privacy and anonymity. Our goal has been to identify and compare a number of PPDP and PPML techniques and evaluate their relative effectiveness against emerging machine learning-based threats.
So now we're going to talk about machine learning threats. Downstream machine learning threats generally involve a form of membership inference, an attempt to recreate the original dataset, or to reveal some sensitive information about the original dataset. The principal ML-associated threats can be described in 6 different attack models listed here. When we discuss these attack models, they're often associated with 3 different downstream scenarios. You can see in the figure here. In the first, it's the model training service paradigm, in which the data owner is providing data and the service provider is setting up and training a model. The second, called model serving paradigm, is where the data owner pre-trains their own machine learning model, which they then upload to a service provider to store and run. Query APIs can then be set up to allow users to use the model and run predictions on the cloud. The third scenario involves the use of both services. The attack models assume that the data owner and the computation party or service provider are always separate entities. And in some attack models, there may also be a third party, an end user, which can also be the attacker. Looking closer at these, data in the clear is the simplest attack model scenario. In this case, the data is stored in its raw form and not encrypted, transformed, or anonymized in any way. This leaves the data highly vulnerable to attacks from inside and outside the service provider or computation party with whom the data now resides. As part of the same category, there's another form of attack called ML model memorization. Here, the service provider is given full access to the data set. The provider can simply steal the data, or they can encode the sensitive data into the trained model using various methods. In the second part of the attack, provided the malicious party has access to the model, as a provider or as an end user, they can retrieve the sensitive information about the data set. In the case of reconstruction attacks, the computation party or service provider doesn't have full access to the data set. Rather, they have white box access to the trained model, including feature vectors. This model is similar to the second stage of model memorization outlined previously. In reconstruction attacks, the malicious party aims to reconstruct the raw data set by using information from feature vectors in the model. Attacks of this nature are often made possible if the feature vectors from the training phase are not deleted afterwards or they're stored in the model. Moving on to model inversion attacks. In these scenarios, machine learning models do not store any feature vectors, so it's just the trained model being uploaded to the service provider. In this attack paradigm, the malicious party is working to recreate the actual feature vectors, or as close as possible to those originally used to create the model. If the attacker has basic white box access, for example, a service provider providing a model serving service, they're able to, and if they're able to identify the model along with algorithm, topology, and parameters, they can then reveal the information from the data training set. Where the attacker has black box access, only the model output can be used by sending crafted samples to the model and using that output or the predictions to learn about the data set. In membership inference attacks, the attacker, a results party, is armed with some knowledge of a target sample. Using black box access to the model, the attacker seeks to infer if the sample is a member of the training data set that was used to train the model. Here, the attacker uses output confidence scores from predictions on samples as a training data set to build another inference attack model. In this in turn is used to predict if the target sample is a member of the original machine learning model's training data set. In order to anonymize sensitive data, the removal or encryption of personal identifiers such as name, ID, or address is common practice. In spite of these efforts, attackers are still able to de-anonymize or re-identify individual records or information using auxiliary information. Data often passes through multiple sources. De-anonymization uses the availability of this public information to cross-reference the anonymized data and reveal identity. In model classification attacks, the attacker's aim is to learn attributes present in the training data set. The process is very similar to membership inference attacks. The attacker is able to build some sort of shadow attack models, both with and without the target attribute. The parameters of these models are then extracted as features and fed into a new classifier, which is used to predict if the model property exists within the original training set.
Here, I will talk about a little about database tools for privacy preservation. Our focus in the paper is on privacy preservation for data that may be accessed by downstream machine learning application, not data at rest in a database. Although data that has been anonymized or encrypted can still be revealed by machine learning attacks, basic anonymization and encryption still form a foundation step in any PPDP or PPML approach. To that end, there exists a number of commercially available database tools that can contribute to this essential step in privacy preservation techniques. And here we have provided some examples of such tools. These provide services such as discovery of sensitive data, data redaction, masking, and encryption. For example, IBM Guardian, Oracle Advanced Security, Solves VDS platform, and always encrypted. In the next slide, I will talk about PPML solution or privacy models. Differential privacy, there is two main categories for PPML, and the first one is perturbation, And differential privacy protects the data when we have multiple input sides. On the other hand, an attacker cannot de-anonymize differential privacy since this method is immune to post-processing. There are three different phases for differential privacy to add noise to the dataset. We can add noise to the input or add noise to the intermediate values and add noise to the generated model. And the second one is LDP or local differential privacy. When the input parties do not have enough information to train and machine learning model, it may be better to utilize approaches that rely on the LDP or local differential privacy. The assumption here is that the data collector is untrusted, so each party adds noise to their data set and publish their perturbed data to the untrusted party. And the last one is dimension reduction or DR. This approach modifies the source data by projecting them to a lower dimension. There is a trade-off. As much as we reduce the dimension, we also increase the privacy, but we lose the utility. And the second approaches is cryptography approach. And the first one is homomorphic encryption. This approach is the most common method in PPML. Homomorphic encryption uses addition and multiplication with the encrypted text and retrieves an encrypted result. And it needs high memory and it's also slow, but it's accurate. And the second one is garbled circuits. This approach allows two parties that do not trust each other to jointly evaluate their secret data without involving a trusted third party. And the third one is secure processor. This approach protects sensitive data from modification or unauthorized access. In this system, each data owner independently establish a secure channel with the code and data, then authentications themselves. And the last one is order preserving encryption. In this method, the encryption function preserves the numerical order of plaintext. This approach is accurate and can combine easily with existing databases.
Now we'll talk about results. Here's a results table that maps various ML-specific attack models to the various privacy models. Check mark in the table indicates that the privacy model is effective against the corresponding attack. For brevity's sake, we'll not go through these by one. Ultimately, there's no catch-all privacy model that can counter all of these various threats. Rather, combinations are required to create a holistic approach towards privacy preservation. A number of observed combinations that we also have seen supported in literature are the differential privacy and dimension reduction, which based on these characteristics, we'd expect to perform better in terms of speed and memory requirements, but less so in accuracy. Homomorphic and differential privacy. The use of homomorphic encryption in this combination would be expected to increase computational resources. And finally, garbled circuits and differential privacy. So when used in combination, these techniques can complement each other. There are, however, also best practices that can be employed alongside these privacy models to reduce potential attack surfaces. Again, for brevity's sake, we can't go into these, but these would include the use of databases, as mentioned earlier, to anonymize or encrypt raw data. Ultimately, employing a balance of these best practices along with appropriate privacy model combinations can reduce attack surfaces exposure to an acceptable level. One of the interesting areas for future work would include additional research on the application of order preserving encryption within the context of downstream machine learning applications. In literature survey, the use of order preserving encryption with machine learning is referenced theoretically. So it'd be interesting to see if this implemented and tested will actually work. Better performance characteristics compared with other things like homomorphic encryption, along with its ability to work with relational databases, makes this a potentially unique tool. Secure processors are still not commonly used in PPML, but show strong promise for performance perspective. Also, because they're not broadly used in this context, they may in fact prove to have broader effectiveness against various attacks than is theorized in our results discussion. Future work would include implementation that attempts to use secure processors within the context of two service paradigms, then test their effectiveness against various attack methods. These are our references. Thank you.